Thank you, everyone. Welcome, and thank you for making the time to hear a little bit about weed biocontrol. And when I discussed with Nigel and Keith what would be the topics that would be of interest for this group, there were many around biocontrol, and I could easily probably fill up your whole year, your whole series with talks about weed biocontrol, but we did have to keep it tight. And so decided to talk about something that would hopefully give you some tools when you encounter weed biocontrol agents, when you encounter the public that are interested in weed biocontrol agents that you see in your pitches, and when people want to know how do you know these agents are safe. So what I'm hoping to do today is to give you a little bit of the scientific backgrounds that sits at the base of how we know agents are safe, and also how much more we are progressing that understanding of safety with science, more current science that we do these days. And I probably have packed too much into this, and we might have to stop partway through the examples that I wanted to give you. But let's get started. I'm building this presentation on the assumption that you know the basics of weed biocontrol, so I'm not going to explain that. So if you're less familiar with the fundamentals of weed biocontrol, then I apologize. When you come across the public and they ask you about biocontrol, I'm pretty sure that the first question you get asked, it's definitely the first question that we get asked, is, isn't biocontrol risky? Haven't we learned enough from the past? Is this biocontrol agent going to be the next stoat and the next cane toad? The short answer is no. And for the rest of the presentations, I will again explain why and give you the tools to engage with the public about why it isn't. Vertebrates, those biocontrol attempts in the past with vertebrates, it's a very different story for a whole lot of reasons that we will discuss. And just as an anecdote, as a side story, I will just inform you that even when those agents, biocontrol agents, were introduced, the scientists have actually suggested this was going to be a very bad idea and predicted the poor outcomes for the native wildlife, both in New Zealand and in Australia. And it was more of a lobby groups and politicians that have decided to bring those agents in. Nevertheless, it's us, the scientists, who have to deal with the question, and yourselves as weed controllers and fighters who engage with the public. When we talk about the risks that weed biocontrol agents can inflict, these are the risks of non-target effects, and we distinguish between direct and indirect non-target effects. Direct non-target effects are the risks that the biocontrol agents will have impact on plants that are other than the target weed, other than the target host species. Those kind of impacts, they can be spillover effects. So when you think about the early days of a program, when the agents are building up, the weed is at high abundance and high density, very high populations of the agents, and then as the weed declines, it takes time for the agents to decline again as well. And so there would be high densities, high abundance of the weed biocontrol agents. It will spill over to the vegetation around it. It will probably try to feed because it's hungry, but it will die off. And so these kind of impacts, they are transient. They are short-lived. On the other hand, there can be persistent direct non-target effects, and such persistent effects, that means that the agent can survive and reproduce on a non-target species, and those kind of effects, they can be significant or they can be minor. Then we have indirect non-target effects, and those are the risks for wider food web and ecosystem effects. And we might get time to touch a little bit on examples of studies on that later. But we'll start with the direct non-target effects. This is usually what people are most concerned about. What will they eat next when they run out of weed? So the concept that we rely on is host specificity, which is very common in herbivorous insects and plant pathogens. We tend to hear more in the news about the likes of brown marmorated stink bug or Queensland fruit fly. These are those insects that have a really broad host range and therefore can be serious pests. But if you think about it, how many insects are around you and you're familiar with? And how many do you hear about that are this devastating, have such a broad host range? This is really the handful of exceptions. The rule is host specificity. And the reason for that is that plants that are closely related to each other use similar chemicals for defenses. And so when insects co-evolve with plants that they can feed on, they tend to be able to evolve mechanisms that allow them to avoid these defenses. When they come across a defense, another type of defense in another plant, in another group of plants, they're not equipped to deal with those other defenses. And so specificity tends to be more common, and the longer host-specific agents have, or natural enemies, herbivores have time to co-evolve with their host, the tighter that specificity becomes. And so most herbivorous insects and pathogens really attack only a single species or a small group of closely related species. And the reason that I've got the picture there of the monarch butterfly caterpillar is that this is an example that is familiar to most people, surely to yourselves as well. And the question I will ask you, and feel free to put something in the chat, what happens when the monarch butterfly caterpillar runs out of swan plant in your garden? What do they do? Where do they go? So maybe very, very quickly put something in the chat, and if someone can share that with me, because I cannot see the chat.
Come on, people, don't be shy. Get typing. Unless you're driving, of course.
Do the caterpillars go onto your lettuces? Do they go onto your pumpkins? Do they go into your coprosma or your hibis, or what do they do?
So we've got lack of food means lack of survival, so numbers drop.
They die.
Yeah.
So this is an example that, again, people are very familiar with and can relate to very easily. So use that. Ask them. They can see that that's something that they have seen, and is front of mind, can be easy for them to grasp. That is host specificity. When they run out of swamp plant, they die. They don't go and start eating the other plants in your garden. And that is the most common scenario in insect herbivory and in plant pathogens. So use that. Based on that chemical similarity between closely related plants, Wapshire has come up with a method for assessing and circumscribing the host range of herbivorous insects 50 years ago. Now, weed biocontrol is a practice that is about 120 years old globally and coming up to 100 years in New Zealand. So host specificity tests have been done from the very beginning, but this approach, the centrifugal phylogenetic approach, has been around for 50 years. And since it's coming on, that has still remained the gold standard and the basis for how we determine host specificity. And in this method, we expose the organism, which is the candidate biocontrol agent, to a sequence of plants from those most closely related to the weed, progressing successively more and more distantly related plants until we can ascertain what is that host range. Is it the species? Is it the genus? Is it the subtribe? Is it the tribe, subfamily, the family? That's how we, by exposing plants that are more and more distant, we can determine what is that host range. Now, on top of those, that centrifugal approach, we add a few more criteria for plants that we will add to the test list. So we will look at plants with biochemical or morphological similarities to the host plant. Other recorded hosts that from the native range or from other places in the world that this candidate agent has been recorded on. If there are pests that are closely related to the candidate agent, we would look at hosts that are related at the hosts of those pests. And then other economically important plants or New Zealand natives that have not previously been exposed. And all of these kind of criteria have also been suggested by Wopsher in that paper from 50 years ago. So we really are basically continuing with that method, and that has served us very well. The number of plant species that we test for each agent varies, and that depends on how many plants are there that are closely related, that need to be tested, that are either economically important or native. And those kind of guidelines for testing have become internationally accepted and best practice and have served us extremely well. How well? Well, let me share with you the safety record for weed biocontrol globally. So again, around 120 years, globally around 600 agents have been released. Only 4 of them have had serious non-target impacts. All of them on plants in the same genus as the target weed, and all of them were predictable from the testing methods that we have today. And so those 4, they are older instances from mostly from the phylogenetic centrifuge, including one of the very early biocontrol programs, the one on Opuntia, on prickly pear, which I'm pretty sure a lot of you have heard about. And when I look at that number 4, if I'm looking at the kind of couple of decades that I've been in the weed biocontrol practice, that number 4 remains there. It's just the percentage that keeps dropping. This bit keeps dropping because there are no additional species that are being found to have serious non-target effects, but the number of agents being released keeps growing. And so it's the same 4, and it's just the percentage that keeps dropping. So there's just no more releases of agents that can have these kind of non-target effects. At the times that those were released, standards of biosafety have been a little lower. We wouldn't have allowed those today. If we think about one of those agents, Rhinocilus conicus, it's the Nordic thistle receptacle weevil, which we have released in New Zealand in the early 70s, 1972. This was released in North America in the 1960s, and it turned out to have serious non-target effects on native thistles in North America. We don't have native thistles in New Zealand. And again, going back, those impacts were predictable from the host range testing, but at the time it was determined that controlling the weed was more important and nobody was going to care about the native thistles. So of course today we do care about the native thistles and therefore we wouldn't do it. But again, the point is that the type of testing we do, the methods we use for testing, we're actually able to predict those non-target effects and have predicted them. And so over time, we have improved testing further to even further reduce the risk for those kind of indirect non-target effects. In New Zealand, we do conduct extensive follow-up surveys to check on non-target impacts. And so again, in close to 100 years of history, we have released 70 agents so far and no significant non-target effects. We have detected some non-target effects. 2 of those instances were unexpected, were a surprise, and we have learned from them and adjusted our protocols based on those instances. And luckily, those non-target effects have all been on exotic species, mostly weedy species. So those are the broom seed beetle and the gorse pod moth. And with the broom seed beetle, at the time of testing, the gold standard for test was what we call choice tests, where we put the candidate agents in a cage with the target weed, broom, and either one or more non-target species. And the agent can show whether which of those species they select, they have a preference for. And it was deemed reliable and practical. And the broom seed beetle in choice tests selected broom. It was released, and after release, it was discovered that the beetle goes on to tagasaste, or tree lucerne, which is exotic again and a weed in places. And what we discovered there was that at the time that tree lucerne flowers and starts producing its early seed pods, broom is not yet flowering. And so in effect, in nature, the beetle is exposed to a no-choice situation. So it doesn't have its host, but something else that is possible for it to develop on is available. So again, luckily, no harm caused here to any plants that are important because they're native or economically significant. But the learning for us was to not rely on choice tests in the first instance, but actually firstly rely on choice tests. On no choice tests. And if we see any feeding and development of the candidate agents in the no choice environment, then we might move on to do some choice tests to try to understand better what is the host range of that candidate. With the gorse pod moth, the population that was tested was from the UK, and it was sufficiently host specific. But prior to release of the moth, it was decided to bring some extra moths from a population from Portugal, same species, and this was to augment the genetic variability. And so after release, it was discovered that the gorse pod moth can actually attack other legumes, other species, again, mainly weeds. And following up on that, was discovered that although the population from Portugal was the same species, and there's no argument about that, the host range of the population from Portugal was actually a little bit broader than the population from the UK. And the learning for us from that was that we have decided that we only release populations that have been tested. So we're not reliant just on the taxonomic status of the species, but we actually confined our releases to populations that have actually been tested. I don't think that is anywhere regulated for. This is our decision, and this is how we have decided to do things and how we have upgraded our best practice. A little bit of science, of more recent science we're getting into, and the science that I'll be talking about now is funded from the Ministry for Business, Innovation and Employment through our CIF contracts and a little bit through B3. This is the underpinning science that we do to improve our practices in weed biocontrol. And before I even start to describe the science to you, and really only a tiny amount of what we've been doing, I do want to share with you that our group here in New Zealand at Manaki Whenua, we are considered the top of the world in that area, and the other weed biocontrolling nations look up to us and adopt the science we do. So something we can be proud of, and we are. One of the areas of novel science that we're getting into is metabolomics. This is something that we haven't got capability within Manaki Whenua to do, but we are combining forces with Massey University, with researchers from Massey. And what is metabolomics? So metabolomics is the study of plant chemistry at the molecular level rather than the gene level. So instead of looking at what molecules the DNA can code for, we're looking at what is actually being coded for, what is the product in given environmental situations. So this is the entire profile of metabolites of the plants. This is called the metabolome. This is not looking at individual molecules, but at that whole profile, the phenotype, the biochemical phenotype. And we've done a review recently when asked what areas of wheat biocontrol metabolomics can serve us in. And one of those areas is in that host specificity, determining host specificity. And there are two sides to this coin. One of them is that we can use metabolomics to add species that are perhaps a little bit more distant phylogenetically from the target weed, but share a similar metabolite profile. We can identify them perhaps through that metabolome and help add them to the list of species that we test. So again, increase safety this way by expanding beyond the slightly beyond the phylogenetic centrifugal phylogenetic approach. The other side of that coin is when we have native indigenous plants that are quite rare or protected, and we cannot obtain them for testing. And here perhaps there is an opportunity, if we can find good enough methods for metabolomics to be incorporated into the testing regime, that we might be able to collect the volatiles, the metabolome, that metabolic profile from those plants in their native environment without having to actually bring the plants themselves into the testing and assess the risk that way. So those are two ways where metabolomics would hopefully in the future help us improve on our host range testing. This technology is still in its early days, and it's not quite at the stage where we can start incorporating that into our testing regime, but we are already certainly thinking about how we would be able to use it, how we want to develop, which way we want it to develop. Another piece of research that I want to describe to you is around the relative performance risk score. So this is from about 10 years ago, but it keeps developing. And the reason we needed this piece of work is because we have become so good in our host range testing at determining what we call the fundamental host range of our candidate agents. So we put them in a petri dish or in a cage with a non-target plant, and they have the choice to either feed or die. And so occasionally they will try to feed on something. If they're not completely rejected, they will try to feed on something, might even develop on a plant that is a non-target. And that tells us what physiologically they can develop on. This is the fundamental host range. But we know that in nature, those agents will be exposed to a whole range of other environmental cues, and they will only end up using a subset of that fundamental host range. It's what we call the ecological host range. And we want to determine what is that ecological host range reliably enough so that we don't end up rejecting agents that are essentially safe just because they had some feeding in a petri dish on something that is within their fundamental host range. So hopefully I've managed to explain it without confusing you too much. And so the way we do that is we've developed this relative performance risk score. And the relative performance is basically asking how well that insect, for example, insect, mite, pathogen, develops on the target weed. And let's say that could be 100% of larvae develop to adult, or 50% develop to adult, or 70% develop to adult. And then there's the performance on the non-target hosts, and that could be 20% develop, or 10%, or 30%. So that 20 or 10 or 30, we don't let it just stand in its own right, but we compare it, how is it relative to the performance on the target weed. So if the target weed, they do 100%, and on the non-target, they do 50%, then the score is 0.5. If they do 70% on the target weed and 35 on the non-target, the score is still 0.5. So hopefully that's clear. If they do 50% on the target weed and 50% on the non-target, then the score is 1. So they do equally well. And if they do 50% on the target weed and 100% on the non-target, then they do better on the non-target. And that's a worry. We've never had that. I don't think so. We look at that relative performance as far as survival of larvae on the non-target and also reproduction. We hope potentially in the future to be able to look at other measures, but for now we didn't have enough data points from case studies in New Zealand. So now that we've got that risk score, we put that on a graph. And so that is what you see on the x-axis here. That is that risk score for a certain, relating to any certain host. And then we look back at past programs where agents are already in the country. We look at how they did in the test, what is the relative score from the tests, and what's happened in the wild. Have they actually made those hosts a host in the wild? And what came out of that is that there is almost a very clear threshold where below that threshold, scores that are below that threshold are telling us that even if there is development in the testing environment, these plants are not going to become hosts in the wild. Not. Whereas above that score, the certain score, you do get those plants are very likely to become, are at high risk of becoming hosts in the wild. And then there is a little bit of a gray area in the middle where more testing is probably required. It's not that clear if there's going to be non-target effects, whether there will be spillover effects or permanent effects, unclear. So this has been a huge progress for us to be able to avoid rejecting potentially safe agents. The EPA has accepted this science and has already several years ago now approved a biocontrol agent for Tatsan, Hypericum and Rosamum, despite that agent being able to feed on and damage a native Hypericum pusillum. This agent is now in early days of establishing. There's still not enough of it in the wild, but we are keeping an eye on it, and we're looking forward to the opportunity to actually test the prediction from the score, from this relative risk score, to see if our predictions stood the test. This has already been adopted in Australia and in the US. They've already tested data sets from their previous programs, and the same pattern persisted. And in New Zealand, this also been adopted now and tested on biocontrol agents for insect pests. So that was done as part of a B3 project, and again, that pattern persisted. So a very, very useful tool. How are we doing on time? Let me know if you want me to stop. We are at 5:30. Do you want me to stop?
How many more slides do you have?
Too many more.
Because people are really, the questions coming in are really specific. So yeah. How much more?
So I was going to go into indirect non-target effects now. Do you want me to give one example there? I won't go into all the others. Maybe let's do one example here. Okay. So with indirect non-target effects, the example I wanted to share with you is a work that is actually still ongoing at the moment. And this is around the old man's beard leaf miner, Phytomyza vitalbi. And there is a native, very closely related species, Phytomyza clematidis, that makes leaf mines on native clematis. Now, the native leaf miner also has a parasitoid that attacks it, and that parasitoid took a liking to the introduced leaf miner. So this is where we've got another trophic level that is being impacted. So it's not about whether the leaf miner attacks native clematis, but it's about a native parasitoid, another trophic level, adapting to a new organism in the environment. So food web interactions. And the question that brought was, well, there's a whole lot more old man's beard leaf miner than there is native leaf miner, because the native leaf miner is fairly rare. And so if there is so much more of the introduced leaf miner, does it mean that the populations of the parasitoid increase that much that the impact that they have on the native leaf miner is potentially putting the leaf miner at higher risk because it is already rare? And we'll cut a long story short here. A study that we're literally doing now, we've found that old man's beard leaves, 25% of them are parasitized, versus only about 1/10 of native clematis leaves being parasitized. Now, there is we've been testing partly up to 4 kilometers, and the reasons for that is because the introduced leaf miner, the biocontrol agent, can fly about up to 4 kilometers, and it needs to feed on old man's beard to be able to lay eggs. So it could have some degree of non-target effect by feeding on old man's beard, flying up to 4 kilometers, finding a native clematis and ovipositing in that. So up to 4 kilometers, we can expect some spillover effect. If the parasitoid goes to those kind of mines, then that effect would be seen up to 4 kilometers away. But we also looked at native clematis that is completely away from old man's beard to see if there's such an increase in abundance in parasitoids. If there is, does it go even beyond that 4 kilometers? Is the impact on the native leaf miner growing beyond that? So what you're seeing in the graph here is the distance from old man's beard and the percentage of miners that are being parasitized and on the x-axis. And long story short, we found no increase in leaf mines, so there's no a spillover effect of the introduced leaf miner on native clematis, and there's no increase in parasitism on the native leaf miner. So the native leaf miner is not suffering additional parasitism pressure because of the introduced leaf miner. If anything, if you look at the zero distance at those natives that are very close to old man's beard, they're actually potentially suffering less parasitism. So it's maybe that the parasitoid is slightly more attracted actually to the introduced and leaving the native alone. So perhaps it's doing the native leaf miner a favor at the close proximity. There's plenty more questions that we could study around that. What are the mechanisms for that we can learn from that would be very useful if we had the funding, which we don't currently. So that is one example of indirect non-target effect food web effects, and I will skip a whole lot of other things that I was going to tell you about just to get us to here. I just wanted to share with you the list of weeds that have agents available for them in New Zealand. You don't need to memorize it. We have that online, and you can quickly scan that QR code, and we will also share the link to that at the end. And the list, you can go into that list, and it lists the weeds alphabetically by common name, and then for each weed, the agents that are available for them. And we are developing agents to these weeds here on these lists. Some of those programs are more active, others more dormant, but generally all of these are somewhat active programs. And this is another tool that you can come back to. We have a page of frequently asked questions on our website, again, explaining the mechanisms behind how we know agents are safe. So do feel free, again, we'll have that link attached to the end of the talk. And finally, the best way to keep up to date with what's happening in our world is through our newsletter. It's a quarterly newsletter. Ron Sprague, who's the editor sitting here in the audience today, is an exceptional science communicator, and this newsletter is very digestible and readable. So I highly recommend, if you're not already subscribed, then do subscribe to the newsletter. And I will stop here and leave it for questions.
Fabulous, thank you. In the link there are, in the chat, there's a whole lot of links that please have a look at. They're from Ronny, which is links to the newsletter and the frequently asked questions and all that information. So people have been flooding with specific questions about weed agents. There was a question about heather beetles doing in Tongariro. Do you have an update on them?
Not extremely recent, but generally after about 20 years of them very much struggling, they have in the last few years started to explode. Seem to be doing very well, killing heather, not killing other plants. We have done a very nice bit of science, and this is a system where a lot of questions have come up over the years, and we've started publishing a flurry of papers around those questions, and we're still in the process. A few more are coming out, at least 2 more will be coming out in the next year, 2 years. And one of them is around how complicated the relationship between biocontrol, the impacts of biocontrol, the ecosystem long-term impacts, comparing 5 years of insecticide and herbicide removal of heather beetle and heather compared to biocontrol, compared to nothing, basically showing that grasses certainly invade after heather, both native and exotic. Broadleaves, herbs survive, natives survive under heather beetle, being damaged by herbicides. And so while both herbicides and heather beetle can reduce heather very well and to about the same degree, the impacts of herbicides on specifically native broadleaves, as well as introduced broadleaves and herbs, make it such that overall biocontrol benefits native biodiversity better than herbicides. Heather looks like heather beetle looks like it comes back. We see some new regeneration of heather in pockets here and there on Central Plateau and Tongariro, and the heather beetles do come back. They find those individual plants or small patches, and they do manage to come back and get on top of it. So that's very, very encouraging.
Brilliant. And now there's quite a lot of chat about Tradescantia beetle. People kind of asking and replying about moving volunteers moving the Tradescantia biocontrol agents. What is your take on that?
With the beetles, if you can collect them separate from the plant, then very easy to move. There's no issues, no biosecurity issues with that. I'm not entirely sure that you can legally move the plants. So that's where your issue can come up. So need to check with the council. If you're allowed to move the plants, you might be able to get an exemption and permission to move the plant for that sake. That's obviously more important with the pathogen, with Cordiana, the yellow leaf spot, or the Tradescantia yellow leaf spot, because you can't really move that without moving the plant. So that, again, needs to be regulated. And there should be a way to do that, but I think there just needs to be communicated with the council to make clear if that's allowed.
And moving other biocontrols, someone was stating that it shouldn't be done if they're just been released. Is that correct?
That is correct. That is correct. We want to see the populations build up to a level where they can sustain themselves well in the release site. And once they're well established, building up populations, only then that would be the time to start redistributing them. Again, the best thing is to communicate with the council biosecurity officers, because they know where the release sites, the first early release sites are, and they can assess. They get training. They come to Manaki Whenua for training, and they know how to assess whether the populations are sustaining themselves well enough and are big enough to be able to start harvesting.
Brilliant. Someone's asking, how do you measure efficacy in the biocontrols? Are these stats available?
Weeds, there are some stats available. It is different for every species of weed, for every species of agent. Very difficult on many occasions to measure. Quite intensive in data collection. We really, because it's so intensive, we can only do that for a small number of what we call flagship programs. Tradescantia is becoming one of them. We expected the damage to be spectacular and quick, and so we have taken a lot of baseline measurements before releasing the agents. Tradescantia is also unique in that instance because we had a target measure for what success looks like. We had data from the native range from Brazil that showing that at 200 grams dry weight per square meter allows, so if Tradescantia is in the area at that level of around 200 grams per square meter, that allows for regeneration to take place. And we knew at the time already that in New Zealand, the biomass was on average about 800 grams per square meter of dry matter. So we knew that we needed about at least three quarters of Tradescantia removed before we can start to see regeneration taking place. And actually, I might sneak in quickly another slide of Tradescantia. So here we've got one of those quadrats that was put in as a permanent quadrat to look at what happens with Tradescantia biocontrol, and you can see the peg popping up here, and you can see how deep it is in a mat of Tradescantia. And you can see after biocontrol here, this is the same peg, and you can see how tall it is, and so how much the Tradescantia has dropped. Tradescantia is still around; it's not gone, but you can see the native regeneration happening as well. So this is an example of somewhere where, specifically a project where we knew what we were aiming for, and we knew what success looks like. And we have got a few other projects more around agricultural weeds, where we have been able to get a little bit more quantitative measure of reduction and success. Thistles, nodding thistle is one of those recent ones. You can go back to the newsletter to some old issues and find online this article around nodding thistle. And there, the things that we found were about 80% decline. If we look at overall all of New Zealand, 80% decline in the densities of nodding thistle. Now, of course, there's variability. There are places where it actually went up, and there are places where it's gone completely. But on average, 80%, which is really spectacular. We also found that at about half of the properties that were surveyed, these are properties that were surveyed pre-release, so some decades ago, and then more recently in the last few years. And in about half of them, less control was required. And in about a quarter of them, so half of those half, no more control was required at all. So a lot less herbicide going into the environment. So
Brilliant.
yeah, we do have some projects where we were able to measure, but not all of them.
Right. So there's a question around engaging with tangata whenua regarding use of biocontrols, and what has their response been?
We are required, of course, to engage with tangata whenua when it comes to putting in applications to the Environmental Protection Authority. So we definitely have to do that. And over the years, we have found that on many occasions, the first response from tangata whenua tends to be, don't bring in any more new organisms. You Pakeha have really messed the environment enough already with all the organisms you brought in. Don't bring any more. When we get the opportunity to hui, to wananga, when there is agreement that the plant is a weed, that it is a problem, then when we look together at what are the options to deal with the weed, with the problem, then it comes up that biocontrol is the, in a way, the lesser evil, and actually the method that is most compatible with Te Ao Māori values. It is intergenerational. It is bringing that balance back to a system that has gone out of balance. And so we do certainly end up getting some groups on board, some groups from opposition to non-opposition. Even if they're not supportive, they become non-opposing. And we are working a lot more now on actually trying to bring Māori on board much earlier in the process. So we certainly acknowledge that coming to tangata whenua at the stage where we've already done all the research and we're going to the EPA and we're saying, can you support this? Sign here. That is not good enough. And that Māori have to be involved way, way earlier, possibly, ideally, from deciding about what weeds we're even going to work on. That is very much work in slow progress, but this is where we're heading.
That sounds great. So just someone was asking about the time frame between those two Tradescantia photos.
I don't know to tell you exactly, but we have seen Tradescantia being decimated within 12, 18 months. And in some places in the Waikato, and not coming back. So we thought that after we've seen such decimation very quick, that there will be a return, and that hasn't been the case. So I don't know how old these seedlings are.
Fabulous. There's quite a few questions of people suggesting weeds, so I was just that need a biocontrol, but I was wondering what is, so you had a list of what you're working on. Yeah. What makes you decide which ones to put more effort into, or which ones get the green light?
So first and foremost, it's the funding, because there are, as you suggested, plenty of weeds that we could work on that would be very good candidates for biocontrol, but we are limited to what funding is available for. Funding for these programs comes mainly from the National Biocontrol Collective, which is a consortium of regional councils and unitary authorities in DOC. And they make the decisions together about prioritizing weed targets. We have got a prioritization framework to assist those decisions, and that prioritization framework takes into account, of course, how problematic the weed is, but also how likely it is to be a good target for biocontrol, because not every weed that is a problem weed would be a good target. Unfortunately, climbing asparagus is one where the problem is huge, but surveys over many years have not identified any potential agents that would be specific enough to climbing asparagus and would not be damaging to crop asparagus. So we're out of wits and on that one. Another component is the cost. So a program that is what we call a piggyback program, a repeat program, where some other country has worked on that weed already and has done a lot of the groundwork, would be a lot cheaper and might end up higher up the priority list because it can be done quicker and cheaper. It doesn't mean that expensive programs that are what we call novel programs, where we're starting from scratch, nothing is known, it's going to be long and expensive. It doesn't mean we don't do them, because if the weed is important enough and we believe that there is a good chance that some good candidates will be found, then we still do that. But it's just going into it with our eyes open.
Brilliant, thank you. There's people are flooding questions about different weeds. I suggest you have a look at that website. It's got the, is it one slide back where you've got the list of things that do have biocontrols?
Yes.
So have a look at that website. So all the questions you've got about specific weeds, if they're not on that list, then there isn't a biocontrol. Yeah, no, they're fabulous. Does anyone have more specific questions about the process for biocontrols and the science behind it? Yeah, there's a lot of things that people want biocontrol for. And I know there's a big group of woolly nightshade people out there that and moth plant that really want those to be done.
They are two very different stories.
Yeah. So the woolly nightshade, people are mentioning that the agent only works in specific conditions.
Correct.
So is there an update on that?
Yes, there is an update, and it's gloomy, shall I say. So you're correct, the lacebug, the woolly nightshade lacebug, only works in shady environments, not so much in sunny environments. It does very well in those shady environments. More recently, unfortunately, we've had an invasion of a lacewing from Australia, and that is a ferocious predator, and it likes our lacebugs. So the woolly nightshade lacebug and the Chinese privet lacebug, the privet lacebug, they are favorite ice creams. So we don't yet know what the full impact of that will be, but yeah, it is a worry. We have come across a lot of struggles in finding additional agents for woolly nightshade. We have an agent that is still undergoing testing in South Africa. There's a group there that works on woolly nightshade, and they've reignited work on before we have, and so we've just gone off and said, okay, you've tested all the Solanaceae crops. Can we just give you a couple more of our natives to add to the test list? So our Poro, Solanum avicularium, and escapes me right now. Sorry. And Laciniatum. Xylophilum laciniatum. And the agent is a flower bud feeder. So you can imagine they have to grow New Zealand native plants in containment and get them to flowers so that the agent can feed on the flower buds. And that has just been a nightmare. We just haven't been able to get them initially to germinate plants. We sent several shipments of seeds. I think we have sent seedlings as well. And they just haven't been able to get them to grow in containment and flower. It is coming to the point where we are trying to find some creative solutions around completing these tests, but there is also some potentially degree of non-target feeding by that agent, so it is a big question mark whether it will be suitable. We might end up having to reject that. We're not quite yet rejecting it, but we might end up having to reject it after all this work. We have had another native range survey, again led by the group from South Africa, but we've had Holly Cox from Auckland Council joining them for a New Zealand perspective, and they haven't been able to find any more promising agents in the range where they've searched in Uruguay. We still think we might be able to find perhaps something more suitable in Brazil, so more native range surveys on the horizon. And we would also like to focus more on pathogens because there may be some potential pathogens, and South Africans haven't really focused on pathogens. They really focused on insects. So maybe there will be some hope in the future, but right now that is a fairly gloomy situation.
Oh, that's no good. There's a question if someone wants to know if they can acquire biocontrol for specific plants.
The way we work with distributing biocontrol agents is that you don't need to acquire them to pay for them. The funding from the councils that comes through the National Biocontrol Collective, this is already your rates. You've already paid for it. Once the agents are established in the region or even in another region in the country, it should be possible through the councils, through the biosecurity officers, to call them and ask how you can obtain a release. And if it is possible, if they are sufficiently abundant in the region, they should be able to give you a release. So you don't need to buy them.
Brilliant. And there's a question about biocontrol agents to attack plant pests such as myrtle rust. Has that been looked at?
We think it's very worthwhile looking at. Funding, again, it's a funding issue. There is certainly a potential there. Researchers, plant pathologists from Brazil have identified potential pathogens that could be biocontrol agents for myrtle rust. And it would be amazing, very good and very smart if we could get funding to develop that approach. Yeah.
And also someone was asking, right at the beginning, you said that we're world leading in this field. So is New Zealand, are we exporting much of biocontrols overseas? I wonder if they mean native biocontrol or if they mean our intelligence, our science.
So our science, our intelligence, obviously, once we publish it in the scientific literature, it's out there. And certainly we enjoy sharing it with the rest of the world. And it's an amazing community. Weed Biocontrol is such an amazing global community. And there is a lot of reciprocation and a lot of sharing of information, knowledge, and agents. As far as native agents, we have never yet exported native insects or pathogens as biocontrol agents. We are currently actually being asked to look at mites on native mites on Chrysilla. This is the first time that this has happened, that we are asked to look at native invertebrates as potential biocontrol agents for the UK. So we'll see how that develops. As far as exchanging exotic biocontrol agents, yes, that's certainly happening. in various directions. So sometimes we export agents and sometimes we import agents that have been worked on by others. Examples: Tradescantia. We've been the first. We were the first country in the world to work on that as a weed, and so many years of work on that program. And once we've had the agents out and well established, Australia picked up the phone and can we get a shipment of those? Can we get a box? And yes, they got a box. Equally, if we look at Whorehound, which is here in the middle column on the slide, Australia have taken many, many years to work on agents for Whorehound, and then we picked up the phone and said, can we have that, please? And we got 2 agents for Whorehound to release here. So what took them quite a number of years took us 18 months.
Brilliant. Now, I noticed that there's 3 different hemlock, blackberry, and bridal creeper in a different colour. Is there a reason for that?
There is a reason for that, yes. So these are weeds where natural enemies have come in on their own accord, not introduced intentionally by the science community, not gone through the regulatory system. So blackberry and bridal creeper, they are rusts that they've blown over from Australia. The bridal creeper one is actually a pretty cool story because this was a weed that we were working on, and this was the agent that we were planning to introduce. And then we do New Zealand surveys before we embark on a biocontrol program to see what's already here. And the first site that was visited found the bridal creeper already there, and so we didn't need to introduce it. Obviously, there was no point going through all the testing because the host range testing, because it was here. We did rely on the testing that was done in Australia to determine that it was sufficiently host specific. And then we had to go through a regulatory process with then IRMA, so the predecessor of the EPA, to denew the bridal creeper rust. So as a new organism that's just self-introduced, we wouldn't have been allowed to distribute it. But having gone through the regulatory process of denewing it, it was no longer deemed a new organism, and it was possible to spread it around as a biocontrol agent. And for hemlock, there's the hemlock moth. Again, I'm not actually sure where it arrived from, but it is highly host specific. It's made its way here, and you can see outbreaks of the moth on hemlock completely stripping it off. But yeah, hemlock is still around, nevertheless.
This has been really absolutely fascinating. I've realised that we've crept over 6 o'clock. So what we usually do is we finish up at 6 and stop the recording, and then anyone who wants to stay on the line and just generally chat and talk is welcome to stay on. So so if you don't mind, I'd like to thank you so much, Ronny, for that fascinating talk. I think we're all really passionate about weeds, and even more passionate about having biocontrols that control them so that we don't have to do it. So thank you so much. That was fascinating.